When a musical string is plucked, the vibration we see isn't just one single wave. The full string vibrates to create a bass note, but smaller sections of that same string vibrate simultaneously at higher frequencies. These secondary vibrations happen in exact mathematical proportions. If the string vibrates in 2 equal parts, it produces a note at 1/2 the length. 3 equal parts produce 1/3, and 4 parts give us 1/4. When mathematicians took these musical fractions and added them together in an endless chain, they created the harmonic series: 1 plus 1/2 plus 1/3 plus 1/4, continuing forever. This leads to a question that feels like it should have a simple answer. Does this infinite addition of shrinking numbers eventually settle on a finite total, or does the sum keep growing until it reaches infinity? At first glance, most people assume it must settle down. As the fractions go on, the numbers we are adding become microscopic. By the time you reach the 1,000th term, you're adding 1,000th. Eventually, you're adding 1,000,000th or 1,000,000,000th. Intuitively, these additions become so small that they should stop affecting the total sum. We're going to follow this common sense assumption that the series must have a finite limit, exactly as Johann Bernoulli did, to see if the logic holds up. Johann Bernoulli, a pioneer of early calculus, started with a clever premise. Let's assume this series actually converges to a specific measurable number. He isolated the harmonic series starting from the second term, 1/2, assigning this infinite sum the variable a. To disguise the terms, he multiplied 1/3 by 2, transforming it into 2/6. He did the same, turning 1/4 into 3/12. This creates a bloated version of the original series. It looks different, but the value is identical. Bernoulli is preparing the board for a second equation that will act as a mathematical foil. This is Bernoulli's secondary series. The denominators here are products of consecutive numbers. 1 times 2 is 2, 2 times 3 is 6, and 3 times 4 is 12. Let's call this series C. This specific format allows for a rare algebraic trick. These fractions can be split into 2 separate numbers, being subtracted from one another, creating what's known as a telescoping series. Using this rule, the first term, 1/2, splits into 1 minus 1/2. The 1/6 becomes 1/2 minus 1/3. 1/12 becomes 1/3 minus 1/4. Suddenly, we have an infinite chain of alternating subtractions and additions. Watch what happens when we add them. The negative 1/2 cancels out the positive 1/2 next to it. The negative 1/3 cancels the positive 1/3. This cancellation cascades all the way to infinity. When the collapse is finished, only the very first number survives. This entire infinite series sums exactly to 1. Bernoulli now has a perfect tool, an infinite string of numbers that he knows, with absolute certainty, equals exactly 1. Now we use that result to build a stack of new equations. If the telescoping series equals 1, subtracting its first term, 1/2, leaves exactly 1/2. Subtracting the next term from that remaining sum leaves 1/3. Subtracting the next leaves 1/4. Bernoulli continues this indefinitely, creating an infinite vertical ledger where every subtraction results in the next fraction of the harmonic series. By stacking these equations, Bernoulli has aligned all his mathematical components. He is ready to add the entire system together to see if the total remains a finite number. To find the final answer, we sum every equation in the stack. On the right, adding 1, then 1/2, 1/3, and so on, gives the complete harmonic series. Since the series starting at 1/2 is a, this column totals exactly 1 plus a. On the left, adding all those telescoping parts perfectly recreates the disguised series we made earlier. Its total value is simply a. This leaves us with an impossible conclusion. A equals 1 plus a. For any finite number, this equation is a physical and mathematical impossibility. No quantity can ever be equal to 1 more than itself. Because the algebraic steps are flawless, the error must lie in our very first assumption. The idea that this series settles on a finite number is the only thing that could be wrong. It turns out our intuition is wrong. The harmonic series diverges. The fractions born from a simple vibrating string will just keep adding up, growing slowly and endlessly, forever.